Alrighty, everyone. We're covering just one topic today, topic 7.7, and we're on page 19. So this is calculating equilibrium concentration. So before we were calculating K values and Q values, and you were provided with the information. You were told like this is the pressures at equilibrium, or these are the concentrations. And in this scenario, we give you your starting amounts, but they don't tell you exactly what's going on at equilibrium, and we're going to use something called an ICE table, initial change equilibrium, to figure this out. ICE tables are really similar to BCCA tables with the limiting and excess reactants and products, but I think that in a lot of ways they're easier than a BCCA table. So let's look at example number 1 together. Suppose you start out with only water gas. Okay, so that means like initially we just have water, and this is a KP, not a KC, so I'm doing pressures in my ICE table instead of concentrations. And I haven't gotten to this part yet, but notice how it's just starting with water, and we have zero pressure, zero amounts of our products, because it told us right now that we're starting with only water, so I'd put 0 for the products at 25 degrees Celsius. And its partial pressure is recorded at 0.784 atmospheres. So if there's only water in there in the beginning and the pressure is 0.784, then that entire pressure was just due to the water because there wasn't anything else in there. What are the partial pressures of each species when the system reaches equilibrium? And we're given a Kp value. Great. So we have initial change in equilibrium. Similar to our BCCA table, we're going to use the coefficients in front of these to state the change that's going to occur. So when we have like the change that's going to happen here is that it's going to be reactants, we're still doing minus, products, we're going to do plus. So we're going to lose reactants and we're going to make products. And the ratio is the coefficient. So this would be 2x, and then we're going to have plus 2x, and then we're going to have plus 1x, or x. And just like I told you guys before when we were doing a BCCA table, what we're saying now is we started with this amount and we're going to reduce it by some bit until I get to equilibrium. And we started with this amount and we're going to add some bit of it until we get to equilibrium. Same here. So at equilibrium, it's what we're starting with, 0.784, and no, it's atmospheres, and we're going to minus 2x until we get to equilibrium. 0 plus 2x is just going to be 2x, and 0 plus x is just x. Okay. Now, we know what the Kp number is, but what is the Kp expression? So I look at my reaction here, and everything's a gas, so I'm going to include all of it, and it's going to be products over reactants. So I'm going to have pressure of H2, and in parentheses, and raise it to the second because there's a coefficient of 2. Pressure of O2 raised to the first, divided by the pressure of H2O. Divided by the pressure of H2O squared. And these are the pressures at equilibrium, and that's what we have right here. But we have a little trick that's going to really make this math easier. So, important for very small K values. And what we mean by very small is times 10 to the negative 4 or smaller, meaning like times 10 to the negative 5, negative 6, negative 7, right? Like if it's a numerically smaller value than 1 times by 10 to the negative 4, then this trick will work. And the trick is that we know K is products over reactants, right? And if K is really small, that means that we have a small amount of product that we made, and So small amount of product and a lot of reactants, like the reactants that we started with, like there's a lot of those that are still left over. So for small values of K, the change or X value, like these X's that I just wrote down, in the reactants is so small at equilibrium that it can be neglected. That the reactant amount is so much bigger than these products amount, that the change in this reactant was so small because we kept a lot of that reactant at equilibrium. That's why this reactant is big and the products are small. That this little bit that we lose, this minus 2x, can be ignored. It can be neglected. Okay? And that makes our math so much easier. And so let's look at this. So I'm going to now replace these values for what I have at equilibrium. So here is the pressure of H2 at equilibrium. So that would be a 2x squared. And then I'm going to times that by x, right? Because that's the pressure of O2. And then I'm going to divide that by 0.784. And everyone, I know what the KP number is, so just keep that in mind. So now I'm going to solve for x. The first thing I'm going to do is I'm going to multiply this up here, and then I can multiply those together, right? 2x squared times by x. So we have 0.784 times by our KP equals 2x to the third. Now I'm solving for x. I'm going to keep going. I'm going to give myself more room, so I'm going to keep going down here. So I'm going to divide by 2. So 0.784 times by the KP divided by 2. That equals x to the third. And then everyone, to get x isolated, we would take the cubed root of both sides. But another way of thinking about that is raising both sides to the 1/3. Okay, so when you have a power that's raised to another power, mathematically what you do is you would multiply them, and that would give you the new power for this item. So if we take 3 times by 1/3, then it equals 1. And so that would leave us with 0.784 times by KP divided by 2, this whole thing raised to the 1/3, which is the cubed root, that would equal x. All right, let me grab my calculator. Okay, so let's just do what's inside of the parentheses first. So I'm going to do my 0.784 times by my KP value up here, 0.0 times by 10 to the negative 42nd. And I'm going to divide that by 2. So that was just what was inside the parentheses. Now I'm going to take this and raise it to the 1/3, or take the cubed root. Okay, so x equals, and looking back at my numbers, I used this 0.784, I used this KP, that was 2 sig figs, 3 sig figs. And so keep that in mind for that. I'm going to give a longer number, 9.22087, whatever, times by 10 to the negative 15. But I think I want to end with final values that are 2 significant figures from that KP. So what was the pressure of H2O specifically at equilibrium, right, at this point? Well, 2 times by, and again, you don't have to do this, I just want to prove this point to you. If we take, this is what x equals, and if we do 2 times by this number, And then I do 0.784 minus that. I still have 0.784. This is so small compared to that item. So the pressure at equilibrium for the water is 0.784 atmospheres. Now let's do the pressure of H2. Oh, and we just got that number because I did 2 times by x. That's what it would be. And so when I did that, when I did my 2 times by x, it gave me this value that I've highlighted on my calculator. So that would be 1.8 times by 10 to the negative 14 atmospheres. And then the pressure of O2 at equilibrium is just the x value. And we have that down here. But I'm going to round it to 2 sig figs. 9.2 times by 10 to the negative 15 atmospheres. Alrighty, so this really small K value times 10 to the negative 42nd, so much smaller than the times 10 to the negative 4. We could make this assumption, and we see that it's followed through, that the amount of reactants at equilibrium is so much bigger than our products at equilibrium. So much so that we could neglect this little bit right there. It made our calculations much easier. All right, let's do a couple more. So, find the equilibrium concentrations of all the species if 0.194 moles of COCl. Okay, so I'm starting off with, oh, and then we have liters here. So concentration, okay, my concentration would be 0.194 moles divided by the 5.8 liters, right? So let me do that really quick. 0.194 divided by 5.8. So I'm going to round it by 0.0334. That's my initial amount in concentration, molarity, of the COCl2. So find the equilibrium concentrations of all the species if this many moles is allowed to come to equilibrium in that container. All right, so it didn't directly say this, but I'm going to make the assumption that we're starting with only reactants and that we have 0 moles/molarity of products. I'm going to use the coefficients in the front to say how this is going to change. So it's going to be minus for my reactants and positive for my products. And then they each had a coefficient of 1, so I have a 1x there. So at equilibrium, it would be 0.0334 minus x, and then 0 plus x, which would just be x, 0 plus x, which would just be x. We are given a K value, and it's really small. It's times 10 to the negative 38. So this is a very small number. It's much smaller than a times 10 to the negative 4 number. So we can make the same assumption that we did before, that we can neglect whatever small change happens on the reactants. Okay? We can neglect that. All right. Great. So we are solving for the concentrations of each of these things at equilibrium. And we know that we know the Kc value, and now I'm going to write the Kc expression. All of these are gases, and so they will all go in my equilibrium expression, but I'm using brackets this time. Concentration of carbon monoxide raised to the first, concentration of Cl2 raised to the first, divided by COCl2. Beautiful. And now I'm going to go and I'm going to plug these in here because this is what they are at equilibrium. So my Kc equals, both of those were x, and then this one was 0.0334. Okay. We're solving for x, so I'm going to multiply the 0.0334 times by the kc, and that's going to equal x squared. So then I'm going to take the square root of both sides. And again, guys, the square root is the same as raising something to the 1/2. So it's like 0.0334 times by kc raised to the 1/2. That equals x. All right, plugging that in. So I took, let's see. I took this value, and I'm timesing it by the kc value that was provided, 7.27 times by 10 raised to the negative 38. And then I'm going to take the square root of that, or raise it to the 1/2. Oops, I put an extra parentheses on there, huh? Yeah. Okay. So I have x is equal to 4.93 times by 10 to the negative 20th. All right, great. So now we know what the x value is, but what is the concentration of each of these items at equilibrium? Well, the concentration of COCl2 at equilibrium, this x is so much smaller compared to this, and so it's just going to be 0.0334. How many sig figs should we do? This was 3 sig figs. That was actually 2 sig figs. This is 3 sig figs, so I'm going to go with 2 sig figs. And so 0.033 molarity. Now, the concentration of CO at equilibrium is going to equal the concentration of Cl2 at equilibrium, because they both have this x value, and we know what that x value is. And so the 2 sig figs, 4.9 times by 10 to the negative 20th molarity. Okay, beautiful. Let's see. I want to look at one without this exception. So I'm scanning for the cases. Like, I noticed that this is really small, and so I know the exception's going to happen there. It's not going to happen here. At a certain point in time, 1 liter rigid reaction vessel contains this, and this. Which of the following describes how the measured pressure in the reaction vessel will change, and why it will change that way as the reaction system approaches equilibrium? This is just a comparison of KC and KQ, or QC, sorry, KC and QC, that you're given all this info, and then you're just going to compare our K and our Q. All of these are gases, so they would all be part of our Q expression. PCl5 raised to the first, PCl3 raised to the first, Cl2 raised to the first, and then they tell us all of this. They say there's 1.5 moles of this guy, 1.5 moles of that guy. They tell us that there's 1.1 mole of Cl2, and then there's 2.5 moles of this one. But the moles are not concentration. The cool thing, though, is that it's a 1 liter container. So concentration is moles per liter. So if these are the amount of moles divided by 1 liter, now it's also concentration, right? 1.5 molarity, 1.0 molarity, and 2.5 molarity. So we can plug that in really quick. 2.5 divided by 1.5 times by 1. And so that gives us 1.6 repeating. So I have a K value and I have a Q value. Remember how we had like our number line and our K value here? And our Q value is smaller than our K value. So we're going to go this way to get to K. And that would mean reactants to products, that we're going to favor this forward reaction in which reactants turn into products. All right, so now let's look at our answer options here. The question is, which of the following describes how the measured pressure in the reaction vessel will change and why it will change that way as the reaction system approaches equilibrium at constant temperature? So we were taking 1 mole, or really this is the ratio, like for every 1 mole of PCl3 and 1 mole of Cl2, we create 1 mole of PCl5. It's like we're taking 2 moles total of a gas, and it's becoming 1 mole of a gas, right? And we know that this is the direction we're going to go, that we are going to be taking 2 moles of reactants that are gases and turning them into 1 mole. So overall, the amount of moles of gas is going to decrease until we get to equilibrium. So if the amount of moles is going to decrease to get to equilibrium, that means that the pressure will decrease, right? Less gas, less pressure. So then that narrows us down to these answer options. And then we said that Q is smaller than K. So our answer is right there. The pressure will decrease because Q is smaller than K. All righty. When we have class time, I'm going to give you an example where we're using these ice tables here. Oh, let's actually, will you guys go back to example number 3 on page 20. And this is what we're going to end on. I know it's really small, so make sure you have your notes out and you're following along. I want to give you an example where we can't make that exception because the K value is not small enough, and we got one here. So let's see what it says. I see my reaction. I see that all the species, whether they be reactants or products, are gases. And then it says the synthesis of CH3OH gas from carbon monoxide and H2 is represented in the equation above, and it tells us what the K value is. It says Kc at this temperature is 14.5. A 1 mole sample of carbon monoxide and a 1 mole sample of H2 are pumped into a rigid, previously evacuated 2-liter reaction vessel. Which of the following is true at equilibrium? All right, so when it's saying, hey, what's going on at equilibrium, I would use an ice table to figure that out. And there are 3 items that I'm looking at in my ice table here. I'm going to be looking at, and do we care, is it a Kc? These are concentrations, so sure. And this was a Kc value. Okay, beautiful. So we have concentration of carbon monoxide. We have concentration, make that a plus sign, plus H2 turns into CH3OH, and then ICE. Okay, beautiful. So a 1 mole sample of carbon monoxide in a 2-liter container. So 1 mole divided by 2 liters, right, moles per liter. So my concentration to start off with is 0.50, because 2 sig figs, molarity. And a 0.1 mole sample of H2 in the same 2 liters. So same deal, we have 0.5 molarity. And this was pumped into a previously evacuated container. So there's no CH3OH that we're starting with. I'm going to use the coefficients to help me identify the change here. So my reactants are going to get smaller, my products are going to get bigger. There's a coefficient of 1 in front of the carbon monoxide. there's a coefficient of 2 in front of the H2, and there's a coefficient of 1 in front of the CH3OH. Great. And then at equilibrium, we'd have 0.50 minus x. We'd have 0.50 minus 2x, and then x. Okay, so based on where we're at equilibrium, what could be true? The first one says that the concentration at equilibrium of H2 is equal to twice the concentration of CO, and that's not the case. There's a times 2 here, but the 0.05 was not a times 2, so that is not one of the items that it could be. Answer option B says that H2, this value at equilibrium, will be less than that one. Now, that is true, and we're going to look at the other ones to see, but this is true because they started with the same amount, and then this is going to be minus x, and this is going to be minus 2x. So we're going to remove more from this 0.5 than we are from this 0.5. So this value will be smaller, and that value will be bigger. Answer option C says that all of this one and this one are the same. No, they're not both equal to x, or they're not both equal to 0.5 minus x. So that doesn't work, and all three of them are certainly not equal. I want to talk you through one last thing. I could have you solve for x if I told you what the pressure was at equilibrium. So that's the last thing we're going to end on. There are going to be questions where it asks you to solve for the Kc, or it asks you about different items here, and it tells you what the pressure is at the end of a reaction, once the reaction has reached equilibrium. All right? So let me just choose a number. I don't know if this works out well, but let's just say 10. Let's say that the question told you that when you got to equilibrium, that the total pressure was, or the total concentration, because we're dealing with concentrations instead of pressure, was like 10 molarity. Okay, like if you added all of these together at the end, like the concentrations all added together would equal 10. So what we're saying is 10 is equal to 0.50 minus x plus, let me rewrite it down here so we have more room. Okay, so we're saying 10 is equal to 0.50 minus x, and then plus 0.50 minus 2x plus x. This positive, I guess, don't worry about distributing that. So 0.5 minus x plus 0.5. So let's add together the values that don't have x in them. So that would be 1, and then minus x, minus 2x, and plus x. Okay, so this minus x and plus x, they cancel. So then we're left with minus 2x. Now, let's do a little rearranging here. What if I add this over here, and then I subtract the 10? Let's give it a decimal. We'll even do 10.0. 10.0. Okay, so then I'm going to add my 2x to the other side. I'm going to subtract the 10. So it would be 1 minus 10. Oh, see, I didn't pick a reasonable number. That's okay. And so that would mean I have 1 minus 10. So it would be negative 9.0. Okay. And then I would divide by 2 to get my x. Negative 0.5. That's what x equals, like negative 4.5, and then you can plug it in here. And so we could plug it in, and then we could see what's going on at equilibrium. All right, everyone. I just chose a random number, and so it didn't really work great in our favor, but I'll make sure that we do at least one, but probably a couple examples together as a class where you're looking at the end of it and it says, hey, all of these added together equals something, and that's how you solve for X, because I know you'll see a couple of those questions on the test. All right, thank you all for your time.